Hello, everyone. This is Dr. Sharif, and today we'll continue our lectures about reinforced concrete design. And within this video, we'll continue about shear design and reinforced concrete beams. We explained in the previous video all requirements for the shear design, and within this video, we'll be dealing with detailed design example. The first example will be this one, and we have a simply supported beam under a concentrated load of 80 kilonewton. This is showing the cross section of the beam. The tension steel reinforcement is 2T16, which is the area is 402 millimeter square. This is showing the span. What is required here? We need to draw the shear force diagram and then design for suitable shear reinforcement. FSU is given as 40 Newton per millimeter square, and FYV, the yield strength of the stirrups is 250 Newton per millimeter square. Okay, so to do the solution, we have to get the reactions. This is very clear. We have 80 kilonewton divided by 2, so it will give us as 40 kilonewton left and right. These are the reaction, and therefore we can draw the bending moment, the shear force diagram. In this case, the shear force is very easy. We'll go up 40 and then we'll go horizontal. Then the 80 will take us to minus 40. And then at the end here, we'll have 40 that will take us to 0. So we have a constant shear value of 40 kilonewton and another 40 kilonewton on the left side. So it is constant. The shear here is 40 kilonewton constant value. So we have to design for this shear force. It doesn't matter here at the face of the support or at a distance d because the shear is constant as 40 kilonewton. So let's start getting the second part of the question about how to design for shear reinforcement. First of all, we have to get the shear stress. Shear stress equals shear force divided by the cross-section dimensions, which is B times D, effective depth. And in this case, the shear force is given as kilonewton, and we need at the end the shear stress is Newton per Newton. So we have to multiply this 40 times 10 to power 3 to change it from kilonewton to Newton. So multiply by 10 to power 3. We divide by the B times D. So this is the shear stress. It is 0.89 Newton per millimeter square. Then we have to compare this shear stress with the maximum shear stress, which is Vmax, which is 0.8 square root of FCU or 5. So 0.8 square root of FCU, in this case, the FCU is 40, so it is giving us 5.05. And we have also, this is greater than 5, so we'll take the minimum here. So the Vmax in this case is 5 megapascal or Newton per millimeter square. So we can see that the shear stress is less than Vmax. It means dimensions of the beams are okay and we can continue for design. The next step is to calculate the VC, shear stresses carried by the concrete. We can get it from this equation. We already explained this equation on our previous video, so you can check it. Okay, will be given here, the link for the video. And let's get the 100 AS over BD. This is 100 AS area of the tension steel, which is 2T16. It was 402 divided by B times D. It is 0.893, less than or equal to 3. It's okay. Again, if it is greater than 3, we'll take it as 3. Then we have to check this part here, 400 over D. It is greater than 1. It means it's okay. I take it as 1.78. 778. If it is less than 1, we take it as 1. Then we can substitute into this equation. We can get the VC in this case. It is 0.82 Newton per millimeter square. Now we have to get the VC plus 0.4, which is the required or the stress carried by the shear, the concrete and minimum lengths. So VC is 0.82 plus 0.4. It will give us a value of 1.22. And then we compare the shear stress that we have it here with VC plus 0.4. We can see that the VC plus or the shear stress is less than VC plus 0.4 and greater than half of VC. It means we need minimum lengths or nominal lengths are required, we can get them from this equation. This is the equation of minimum links or minimum stirrups. ASV is greater than or equals 0.4 BVSV divided by 0.95 FYV. And again, to understand what is the meaning of this, you can go and see our previous or first video about design of shear in reinforced concrete beams. Now, BV is known, FYV is known, so the only unknown SCV and the ASV. Let's assume the ASV, we will use two-legged stirrups of 8 millimeter diameter mild steel bars. If we have two legs of 8 millimeter diameter, the area of the 8 millimeter diameter is 50.25 millimeter square multiplied by two legs. So it will give us the total ASCV is 100.5 millimeter square. So now the ASCV is known. The only unknown will be the spacing between stirrups. Let's substitute into this equation with all values. So we'll find now, rearrange, and we get the SCV is less than or equals 298 millimeter. We have to check this one, compare it with the maximum spacing. The maximum spacing is 0.75 D. 0.75 times D is 169 millimeter. So we take the minimum of the two values because the spacing shouldn't exceed the maximum spacing. This is the maximum spacing, 169. So this will govern, 169 will govern, but we cannot take it like that. We have to round it down to the nearest 10 or 25 millimeter. So here I round it down to the nearest 25 millimeter. So it will be use R8 or diameter 8 millimeter spaced at 150 millimeter through out the whole length of the beam. So this example shows us that this beam, which is also a small beam, it needs only minimum shear reinforcement or minimum length throughout the whole length of the beam, and will be R8 spaced at 150 millimeter. And as you know, R refers to mild steel. So it is diameter of 8 millimeter spaced at 150 spacing throughout the whole length of the beam. Now let's go to the second example in this video. Now we have a longer beam, 6 meters, and the cross section is bigger, and we have uniformly distributed load on the beam. FCU is given, FYV, column width. This column width here also is given, and it is required to draw the shear force diagram and then to design the shear reinforcement for this beam. In this case, we have a uniformly distributed load. Therefore, when we calculate reactions, this is the F, or the resultant of the force, equals the load multiplied by the span. So this force here equals 75.2 multiplied by 6. We divided by 2 to get the reaction left and right, and this is the reaction, and therefore we can draw the shear force diagram. In this case, the load is uniformly distributed load, and the shear will be linear. The maximum shear force, it will be at the center line. It is this value. And now we need to get as the shear is not constant, as in the previous example, it was constant. Now it is not constant, it's decreasing when we go through the beam towards the mid span. So we need to get the shear force at the face of the support, and we will use it to compare it with the Vmax. And then also again later we will get the shear at a distance D from the face of the support, and we use it for the design, for the links. So let's start by getting the shear force at the face of the support. At the face of the support here, at distance, which is equals width of the support divided by 2. So the shear at the face of the support equals the reaction, which is 225.6, minus the load multiplied by the distance, which in this case is the support width divided by 2. So in this case, it is 0.15 because the width is 0.3 meter, and half of that one, it will be 0.15. So the shear stress at the face of the support will be less than 225.6. It will be 214.32 kilonewton, and this is logic because when we go towards the center line, the shear will decrease. So now the value at the face of the support at this point equal 214.32 kilonewton. Now we can get the shear stress at the face of the support. We will divide this value by the B times D. So the shear stress at the face of the support equals the P face divided by BD. Don't forget to multiply the shear by 1000 to make it as Newton instead of kilonewton. And therefore, the shear stress at the face of the support is 1.3 Newton per millimeter square. So what should we do now? We need to compare this with the V max. V max is the lesser of 0.8 square root FCU or 5. In this case, because the concrete strength is 30 megapascal, it governed, the first part governed as 4.38. And we can see that the V at face is much lower than the V max. It means dimensions are fine, and we can continue with the design of the links or the stirrups. Now, the first step to do, we have to get the VC, the shear carried by concrete by the concrete VC, or we can also start by getting the shear at a distance D from the face of support, because anyway we will need it also. So let's start by getting the shear at the distance D from the face of the support. So to do that, it will be similar to what we did at exactly at the face of the support, but now it will be at a distance D. So again, it will be the reaction minus uniformly distributed load multiplied by the distance. In this case, the distance equals the support width divided by 2 plus D, because we want to get the shear at a distance D from the face of the support. So the whole distance from the center line will be equal D plus support width divided by 2, which is 0.15. The effective depth of the beam, it was 0.55 because it was 550 millimeter. So now we can get the shear at a distance D from the face of the support. It will be 172.96, which is less than, of course, 225.6. This one we will keep it now because we'll use it to get the shear stress at the face of the support. So let's do it. V at distance D equals V capital at distance D divided by BD. We do the same as we did in the previous slide, and we get it as 101.05 Newton per millimeter square. This one we'll keep it because we'll compare it again later with VC plus 0.4. So now let's get the VC. VC will get it from this equation, which we explained in the previous video about shear. And in this equation, we have to calculate this 100 AS over BD, 400 over D. Let's do that. The first part here, we can see it is 0.595. And the area of the steel reinforcement here is the area of the shear or area of the tension steel reinforcement at the critical section when we calculate shear. In this case, for that beam, we have 2 bars only at the critical section, 2 bars of diameter 25. So the area will be 2 times 491. It will give us 982. So this value here is equivalent to 2 bars of diameter 25 millimeters, because we have 2 bars extended to the end or to the shear section, and 2 bars were shorter, so only we take the area of the tension steel bars at the shear critical section. So this is half of the area of the total steel at the midspan in this case. Now the value here is 0.595, less than 3. It's okay. And also we calculate 400 over D. Now in this case, 400 over D is less than 1. So we use 1 in this case because it shouldn't be less than 1. So if it is less than 1, the code says that use 1 in this case. So we'll substitute 400 over D by 1, 100 AS over BD by this value, and we put the value of FCU. Gamma M, as you know, is 1.25. Putting all of these values, as you can see, will give us a VC, shear stress carried by the concrete, is 0.54 Newton per millimeter square. Now we can calculate the VC plus 0.4. VC plus 0.4 equals 0.94. The VC plus 0.4, as I explained, it is the shear stresses carried by the concrete and the minimum lengths. So we can see here that the shear stress at a distance D, which is 1.05, which is the critical section, is greater than VC plus 0.4. 1.05 is greater than 0.94, and therefore we will need to design for lengths. Lengths are required more than the minimum, yes, more than the minimum, and we have designed for them. So we have to use the equation for that, which is this equation. ASV is greater than or equals BV SV times V minus VC divided by 0.95 FYV. The V small here will be at the VD that we just calculated, 1.05. VC is 0.54. BV is known, which is the width of the beam. In this case, it is 300. And FYV is the yield strength of the links. And the ASV, it will be the area of the links. We have to assume the ASV, and we therefore will be able to get the spacing. Let's do that in the coming slide. Let's assume using diameter 8 millimeter links. So the ASV of two legs in this case will be 100.5 millimeter square, which is 2 multiplied by the area of 1 bar of 8 millimeter. So it will give us this area. Let's put it here, substitute with other values. So the only unknown here will be the SV, and the SV in this case will be less than 156 millimeter. So let's say about 150 millimeter. And also we have to compare it with S max. S max is 0.75 times effective depth. So we take the minimum of the two values. So here we will use R8 or diameter 8 millimeter is based at 150 millimeter spacing. This is the design of the shear reinforcement or the links at the critical section, which is at a distance d from the face of the support. Now, as you know, the shear here in this beam was linear. So when we go through the beam close to the center line, the shear is less, and therefore we don't need this value or this spacing here. So also at the middle part of the beam, we can use nominal lengths. For the nominal lengths here, we use this equations that we used in the previous example. So let's use the same, and also we'll use two-legged stirrups of 8 millimeter. Substitute, we can get the spacing is 198.9 millimeter. We round it down to R8 is based at 190, which is again, the spacing here is less than S max, so it's okay. So in this beam, we have two different configuration of stirrups. Close to the support, we will use R8 is based at 150 millimeter. And at the middle part of the beam, we will use R8 is based at 190 millimeter. But now, how to get where to use this part exactly and where to use this part exactly? We need some more calculations to do that. Let's see together. This is the shear force diagram. We have the V face, we have the V at the center, and also we have to get something called Vn. Vn is the shear force that will be carried by the minimum lengths plus the Vc, or the shear carried by concrete plus minimum lengths. So if we get the Vn and we have the Vc, V face, we can get this distance x here by similarity of triangles or even by a small equations that we are going to see now. What is the V capital N? V capital N is the shear force carried by the minimum lengths plus Vc. So to do that, the Vn equals Vc plus 0.4, okay, which is the minimum, Vc plus 0.4 multiplied by B times D. So let's do that and divided by 1000 to have it as a kilonewton, because we draw the shear in kilonewton. So it will give us a value of 155.1 kilonewton. This is the Vn. After this value, or when the shear is less than this value, from this point to that point, we can use the minimum lengths. Okay, so now we know the Vn, we need to get the x. The x is very easy to get it. It is V face minus Vn divided by the uniform distributed load. So x here equals V face minus Vn divided by W. V face we already calculated before, and Vn we just calculated now. And the uniformly distributed load was 75.2 kilonewton per meter. So get the difference between the shear forces divided by the uniformly distributed load, you get the distance here, which in this case is about 0.8 meter. So because of symmetric, we have 0.8 here and 0.8 here, and therefore we can subtract x plus x here from the total distance that we have it here. We can get the distance in the middle part. We can do that. So the distance in the middle part here will be 4.12 meter. Now, how to get the number of links if it is required from you? It is easy. You know the spacing here in the middle part was 190 millimeter. So to get the number of links, you divide the distance by the spacing. So the number of nominal links or minimum links here, it will be the distance 4.12 meter divided by the spacing, which is 0.19 meter. So it will give us about 22 links. And in the first part here, left part and right part, also we can get the number of links. It will be the distance divided by the spacing. The spacing here, it was 150 millimeter. So it will be 0.79 divided by 0.15, which is 150 millimeter, but we put it in meter. And we round it up, so it will be 6 links and 22 links. So the total number of links will be 6 in the left side, 22 in the middle, and another 6 in the other left side. We can get the total number of links will be about 32 links. This is not required always in questions, so you may not do that. You can just know the distance of X here and here and the spacing, the distance between them, and then you can draw the cross section or the elevation of the beam showing the lengths. So, and showing the distances. So the first part of the beam about 0.8 meter, the last part 0.8 meters. We'll use R8 is based at 150. And if you want to be to put the number of links also, you will say 6. R8 is based at 156 is the number of links. Okay. And R8, it means mild steel of 8 millimeter diameter, and the spacing is 150. The same here and the same in the other side. In the middle part, we'll use minimum links, which is R8 is based at 190, and the number of links also is 22 millimeter. This will conclude our video today. If you like the video, please don't forget to like and subscribe and share it with others. Thank you for watching and see you in a coming video, and goodbye.